In a couple of recent video articles, I demonstrated how to harness LangChain autonomous agents to answer complex questions, or multi-step questions. These steps leverage tools, which are sets of custom functions supported by a clear description of their purpose and parameters. By doing this, the LLM can intelligently determine which tools to use and in what sequence, allowing for the output of one step to serve as the input for the next. This results in a streamlined process to get to a final answer through a series of parallel or sequential steps. Well, while this method has proven effectiveness, its implementation in business scenarios with diverse and voluminous data has raised some concerns about efficiency. In some cases, obtaining the correct answer can even take several minutes. Additionally, there have been instances where the number of generated tokens unexpectedly surpassed the token limit of our OpenAI deployment. The purpose of this article is not to discourage the use of LangChain agents, of course, but to enhance your understanding of possible alternatives to be integrated in our solution. To achieve this, today I will explore the native function calling feature of OpenAI, which, despite necessitating extra manual steps, provides us with insights into potential performance and quality optimization over the current LangChain libraries. This notebook serves as a practical demonstration of how OpenAI's function calling feature operates. Let's dive into the first question, where it's crucial to note some key points. First, we are dealing with a trio of questions bundled together. These questions are entirely independent of one another. In other words, each can be answered in parallel. And an LLM relying solely on its built-in knowledge would be sufficient here, as these questions either require access to private data or public current events or mathematical capabilities that are not natively integrated in OpenAI. To address these points, I've crafted a few straightforward Python functions showcased in the next second cell of this notebook, some of which are designed to resolve the three questions presented. These functions are intentionally simplistic for this demonstration. For instance, the number of flights is represented by the number of days between two dates, assuming one flight per day. And the birthday of my cat is calculated as today's date minus 10 years. The simplicity of these functions also serves to transparently verify the accuracy of our results. And now you may be wondering, but if OpenAI can't directly answer any of these questions, why do I need it? Well, let's think about this point. The questions we receive are typically in an unstructured format, which requires to extract relevant information to populate the arguments before invoking the functions. Moreover, some questions cannot be answered in parallel, but must be orchestrated sequentially. And finally, after each function executes, someone needs to compile the individual results and present the final answer in a conversational manner. And it's precisely this ability of doing process orchestration, entity extraction, and natural language response generation where OpenAI excels, right? So let's take a look at how we can leverage OpenAI to streamline this workflow. Before we delve into our code, let's take a moment to review how the eval function operates in Python. This function is particularly powerful for our purposes because it enables us to execute code that's passed as a string. As you see here, if I run this cell where the Python instruction is provided as a string, it's actually executed by the eval function. This capability will later prove crucial when we pass to eval, rather than a single instruction, the name of a whole function, along with the required parameters. Consequently, we receive the output from executing that function, as illustrated in the following cell. Now, to empower OpenAI to intelligently select the appropriate function and corresponding parameters, we must define them within a dictionary list, which I'm associating to the tools object. And remember, The quality of the function and parameters descriptions directly correlates with the accuracy of the answers we receive. There is a straightforward syntax for this setup which is fully documented on the OpenAI website. Given the accessibility of this information, I will not delve into the syntax details here. Instead, we'll focus on how to effectively use this dictionary list to facilitate the decision-making process for OpenAI. We are now set to make an inaugural OpenAI call. As depicted, we passed the user's question within a standard dictionary. This call not only identifies the query as my question and specifies the model, here GPT-4, but crucially, it also incorporates the tools list containing the tools dictionary that we previously built. Finally, by assigning the auto value to the tool choice parameter, we instruct OpenAI to autonomously select the most appropriate function from our list. Let's run this cell and see how OpenAI handles our request. The response from OpenAI at this stage might not seem like a final answer, and that's because it isn't intended to be one yet. The finish reason parameter returned by this first LLM call is set to tool calls, which signals that there are subsequent steps to follow. Specifically, it indicates that we are to invoke the three functions listed: the get flights, elevation to power, and the my cat born date. Let me more clearly display them in the next cell. One really remarkable thing is that OpenAI has successfully identified which functions are necessary to address our query. And this is no small feat. Beyond just selecting these functions, OpenAI has also extracted and assigned the relevant values to each function's arguments. In essence, what we've received from OpenAI is an actionable blueprint. It's a detailed list of functions complete with the parameters we need to execute them. This structured response is akin to an assistant, providing us with a classic object dictionary that we can now utilize to move forward with confidence. As you might anticipate, the subsequent step involves executing these functions with their designated parameters, leveraging the eval function that I've previously described. I'm performing this action within this cell, primarily for debugging purposes, to demonstrate that the three newly generated dictionaries not only encompass the names of the functions, but also include the outcome, the result of each function's execution. In the next cell, we synthesize all the information we've gathered into a single organized sequence. User message, this is where it all begins. It contains the initial query we posed, forming the foundation of our interaction. First assistant message, OpenAI generates this message. It's a strategic response that lists the three functions and their parameters we'll have to call. And tool messages. For each function the assistant identified, we must provide a corresponding tool message. And since there are three functions, as we said, get flights, elevation to power, and my cat born date, there will be these three tool messages. So each tool message includes the unique identifier of the function and holds the function's result. Altogether, all these messages form a comprehensive list of 5 items: user, assistant, and tool, that we will feed into the next OpenAI call under the messages parameter. When we make this second call, if the finish reason parameter in the response comes back as stop, as it's now, it signals that we have reached the conclusion of our process. At this point, we are equipped with the necessary information to compile and deliver the final answer to our client. Indeed, the process has come full circle, and we can now share a comprehensive and precise response that aligns with the initial query. Flight information, an exact tally of flights aligns with the number of days between Christmas 2020 and the next Easter. 100 flights mirror the duration between these two events. Mathematical confirmation. The calculation provided is accurate. For those who wish to verify, the Windows calculator can serve as a tool. And cat's birthday. The function has accurately determined that my cat's birthday was indeed exactly 10 years ago. In order to round out this presentation, there are two crucial aspects that warrant our attention. Firstly, I aim to validate this implementation against a more intricate query. Instead of tackling three separate questions, we now confront a singular yet more sophisticated query. Calculate the number of flights between Christmas and Easter, raised to the power, and multiplied by the number of days since my cat was born. Now, since my query is now more complex, I integrated it with a so-called system message that facilitates the LLM reasoning process. This query interweaves elements from all the three preceding questions, making it evident that a full parallel execution is unfeasible due to the sequential dependency of each sub-question's output. And of course, upon executing this complex query in our code, we'll observe a notable increase in the number of steps required, nearly doubling the token count and extending the execution time. Secondly, it's imperative to refine our code to ensure its robustness across various degrees of question complexity. In the previous example, with the three independent queries, we achieved our goal with just two queries, or completions to the LLM. The reason why I wrote this while loop is that persists until finish reason equals stop is that, as I demonstrated earlier, if we receive an assistant response with a finish reason that is not stop but tool calls, then it becomes necessary to generate an additional tool message for each function that the assistant identified, which we fill with the response calculated with the eval function. Now I don't want to bore you with the implementation details, which you can find in my public repository at this link. As you can see here, the execution has finished in about 1 minute. Let's quickly review the final set of responses along with some additional features I've added to enhance the readability of the output. To achieve this, I utilized the HTML code to make the lengthy reasoning process more straightforward. If you simply copy and paste this output into Microsoft Word, you will obtain a beautifully formatted text with various levels of headings, colors, and other formatting features. This formatting allows us to analyze each part of the reasoning process individually. Firstly, we have the identification of the high-level steps provided by the initial completion call. Then, we have the remaining steps, some of which can be executed in parallel as these functions, while others must be executed sequentially. And finally, we reach the ultimate result, which displays the correct answer along with a summary of the process it followed. To summarize, I think that this exemplary outcome confirms the effectiveness of function calling. It illustrates how AI can provide clear, correct, and useful answers. And our samples confirmed the reliability of those responses through practical verification methods. Thanks for watching. Arrivederci. And by the way, I don't have a cat. I have a dog, Molly.